Hi everyone. Hi everyone. Welcome back to the channel called Engineering Beyond Blueprint. In our previous video, we talked about electromechanical component and their interview question patterns and how to we should answer for those questions. So today we are rightly jumping into the active components, definition of active components, and then we're going to talk about what are the different types of active components and so on. Right, with that, let's get started. There are three types of discrete components, we would say. One is diode, and other one is transistors, and third one is thyristor. Right, when it comes for diode, there are three types of diodes. One is Schottky and Zener diode and TVS diode. So let's understand the practical application where the Schottky diodes are used. The Schottky diodes are high efficiency DC to DC converters due to low forward voltage drop, right? And Zener voltage are basically used for voltage regulation, reference voltage generation, and ESD protection. Next comes TVS. TVS means is a transit voltage suppression. It's basically used in protecting the data lines from spikes, right? Next comes transistors. So in the transistor also we do have three categories. One is called BGT, which we say bipolar transistor, and second one is called MOSFET, and third one called IGBT, right? So BGT practical application, like they used in low noise amplifier audios, simple switching, and line regulators. So MOSFETs are used in high frequency switching power supplies, right, called SMPS, and drivers and logic gates. The IGBTs are practical application used in high voltage and high current switching electrical vehicles and solar inverters. Third one comes thyristor. Thyristor is called SCR or triad, right? AC power control, light dimmer, and soft starter for heavy AC motors. So these are the practical application these components are being used. The tier B components are called analog integrated circuiter. So these are all nothing but called nerves of the board, right? These process continuous signals, right? So again, in this we do have majorly two categories. One is called Op-Amps, operational amplifier we say in other words, and second one come PMIC, which is nothing but power management integrated circuitry. Operational amplifiers used for sensor signal conditioning, amplifying weak signals from temperature or pressure sensors, right? Power management integrated circuits are nothing but LDOs, which is called load drop out regulators, and buck boost controller to manage the battery life, uh, portable devices basically. Tier 3 component we say like is a digital or logic ICs. These are nothing but a brain of the board, right? These process binary data basically. So when I say binary data, these are all components categorized as a microcontroller unit and FPGA or ASIC. So these are very critical component in nature, right? So microcontrollers are central brain of washing machine, drones, and microwaves. And FPGAs are high-speed parallel processing for video streaming and telecommunication, right? So next, understand what is mean by, I mean, what are the critical parametric data for each of these active components, right? So these we were component engine brings value. Choosing between BGT, MOSFET, and IGBT is rarely about reference and always about physics and efficiency. So I'll just bring this in the comparison table form of view. So let understand the difference between BGT, MOSFET, and IGBT. So as a parameter of control method, right? Control method of BGT is called current control. Basically, in BGT we are using for current control application. Example: base current controls the collector current, right? The MOSFET is used for voltage controlling devices, and this is basically used for gate source voltage to control the drain current, right? Next comes IGBT. IGBT is again we called voltage controlled. Again, this is used for voltage gate emitter controls the collector current. So next comes as a input impedance. BGT are low impedance, draw continuous power, whereas MOSFET are high impedance, draws negligible current. Whereas last one called IGBT, IGBT is very high, easy to drive like FET. Like next comes switching speed, moderate to slow, whereas MOSFET is fastest, can switch at megahertz. Likewise, IGBT is moderate, limited by current tails. Okay, on-state loss defined by VCE at saturation in BGT, whereas in MOSFET defined by RDS on resistive, whereas in IGBT defined by VCE saturation constant drop. Voltage handling low to medium, which is nothing but less than 1 kilowatt. In MOSFET, we would say low to medium at less than 600 volts, whereas in IGBT it's high, which is greater than 600 volt up to 6.5 kilovolt. So next comes as a comparison to between operation amplifiers called bipolar versus CMOS, right? So in parameter wise, input bias current is nothing but IB. Bipolar input operation amplifier is high, nanoamps to microamps range, whereas CMOS operation amplifier extremely low, which is picoamps in range. Input offset voltage is nothing but VOS. Okay, low, better precise in BGT, whereas MOSFET operation amplifier moderate, high drift. When it comes for noise, um, low voltage noise at En, whereas in CMOS operation amplifier higher one fourth one divided by as a frequency in noise. When it comes for application, BGT amplifiers used to wear low noise audio precision instrument, whereas CMOS operation amplifiers used in high impedance sensor at pH probes called buffers. So third come engineering recommendations and alternative solution. When recommending an alternate solution, we also known as cross reference, right? As an engineer looks for parametric equivalence or functional supervisory, we rarely replace the part for part without analyzing why, correct? So here are three common scenarios where I would recommend alternate based critical parameters. Scenario 1, right? Improving efficiency in battery device. How do you can improve efficiency in the battery, right? So original design use BGT for switching a load. Engineer recommendation replace with logic level MOSFET. Reasoning: drive current. A BGT requires continuous bias current, base current called IB to stay on. This wastes the battery life. A MOSFET use almost zero gate current. And third parameter comes voltage drop. If BGT has a VCE saturation of 0.2 volts at 1 amps, it burns 200 milliwatts power. A MOSFET with low RDS on of 20 milliamps at 1 amps burns only I square R equal to nothing but 20 milliwatt. So if you comparatively see 200 milliwatt to 20 milliwatt. So that's where we are recommending MOSFET. Critical parameters checks ensure the MOSFET's threshold voltage is compatible with logic level. Example, less than 3 volts for a 3.3 microcontroller unit. As a scenario B, high voltage motor driver over 400 volts. Original design use high voltage MOSFET. Engineering recommendation replace with IGBT. The reasoning: conduction loss at high voltage, example 600 volt. MOSFET requires very thick silicon resin, leading to massive RDS on. This causes high heat, right? Saturation as another parameter. If you see, an IGBT behaves like a BGT when on, maintaining the constant voltage drop, which is nothing but VCE, approximately 2 volts, regardless of current. Correct? At high power, the IGBT runs cooler than high voltage MOSFET. The critical parameter check, right? Check the switching frequency. If application run greater than 20 kHz, stick to the MOSFET. If less than 20 kHz, typically for motors, the IGBT is superior. Next comes scenario C, where supply chain shortage of operational amplifier. Original design is precision bipolar operation amplifier is out of stock. Right? Engine recommendation propose a zero-drift CMOS operation amplifier, chopper stabilized. Reasoning: standard CMOS amplifiers are usually too noisy or imprecise to replace the bipolar ones. However, zero drift architecture actively corrects offset errors, often outperforming original bipolar part in DC precision. Right? Critical parameters checks, right? Watch out the bandwidth and clock noise, right? Chopper amps have internal switching noise that might affect sensitive RF circuits. How this help engineering workflow? So one is selection, right? You define the constraint, speed, power, and the cost. Comparison: you have to like isolate 2 to 3 parameters that physically matter. Example, RDS versus the thermal resistance. Cross reference: you find alternate not just by matching the datasheet but by matching the application intent. With that said, I hope this session has a brief introduction about active components and their different types of active components by tier 1, tier 2, and tier 3, and types of those tier 1, tier 2, 3 subcomponents also we analyzed. So I want to kind of in the next video to get into deeper for such of these components and their parameters, understand in detail while we are recommending an alternate solution. With that said, do like, subscribe, and motivate with your feedback, so that I would like to bring more such videos which could help you to understand in the near future. With that said, thank you so much for watching again. Have a great day.